So, when you watch a car crash in an action movie, or even if you just accidentally drop your phone onto a hard tile floor, it feels like pure, unpredictable chaos. I mean, you hear the crunch, you see the glass flying everywhere, and it just looks like a completely random mess of destruction.
Right. Yeah. Our brains naturally process it as this totally random event,
Yeah.
like an explosion of variables that no one could possibly predict. We look at the shattered screen or the bent metal and just, chalk it up to bad luck and physical chaos.
But underneath all of that apparent chaos, there is actually a set of rules so precise and honestly so incredibly elegant that they govern every single impact in the entire universe. Those invisible laws dictate everything from that drop smartphone all the way up to two planets colliding in deep space.
Welcome to another deep dive. Today we are unpacking a really fascinating presentation called The Mechanics of Impact, sourced from a creator known as Dice Learning Stuff.
Yeah, it's a fantastic deck. And just to set the ground rules right away, this deep dive is for absolute beginners. You don't need any advanced math degrees for this. Our mission today is to translate this rather intimidating looking slide deck into everyday language so we can look past the dense formulas and understand the beautiful, simple rules governing every collision in the universe.
Absolutely. It's a perfect topic because it strips away all that visual noise of a collision. And, well, if we look at the first slide here, which just shows two simple spheres colliding, it really sets the stage. We are about to explore the invisible laws tracking the paths of everything, from a microscopic particle to a massive asteroid. The rules simply do not change based on scale.
Right. So, indicating that we are moving to the next slide now, slide 2, we get into the quantity of motion or momentum, which is P equals mv. Now, for the absolute beginners listening, think of it this way. Imagine you were standing at the end of a long hallway.
Okay, I'm picturing it.
Someone rolls a really heavy bowling ball toward exactly where you're standing, but it's creaking along. You could just stop it with your foot, right? It has a lot of mass, but very little speed. But now someone fires a tiny glass marble at you, but it's moving at the speed of a bullet.
Right, yeah, and both of those objects possess momentum. They just have different combinations of their mass and their velocity. I really love how the slide phrases this. It calls momentum the fundamental currency of moving objects.
The currency.
Exactly. In the physical universe, when objects interact or collide, momentum is the exact currency they trade. The bowling ball and the fast moving marble possess different denominations of that currency based on how heavy they are and how fast they're moving, but they both carry a balance.
Okay. Indicating we are moving to the third slide. Slide 3, the engine of change. Wait, didn't we all learn F equals ma in school? Force equals mass times acceleration. Why is that explicitly crossed out on this slide?
Yeah, we're doing a little bit of myth busting today. We are actually looking at Newton's true second law of motion in its most complete form. Sigma F equals dp over dt. So force isn't just mass times acceleration. It is the rate at which momentum changes over time.
Oh, wow. So if I have a certain amount of momentum currency, force describes how fast I am emptying my wallet, or I guess how fast someone is handing me cash.
What's fascinating here is that it brings time into the equation. It's not just about pushing hard. It's about how that push alters the object's total motion currency over a specific period. Force is the engine that dictates how quickly that currency is spent or gained.
I mean, that makes total sense when you think about it like a bank transaction.
It really does.
Okay, let's move to the next slide. Slide 4, which is about impulse. There is an image of a baseball bat striking a ball here. Okay, let's unpack this. What exactly is this J equals delta P equals F delta T thing?
Well, look at the graph on the slide. The force doesn't build up slowly. It sits at zero. And then in a microscopic fraction of a second, the force jumps to this massive, incredibly high peak, and then instantly drops back down to zero the moment the ball leaves the bat.
Right, because they are only touching for a split second.
Exactly. Impulse is that total change in momentum. It's the raw force of the hit multiplied by the microscopic duration of time the bat and ball were physically touching.
So wait, let me try an extreme analogy. If I gently push my broken down car down the street for a full minute to get it rolling, versus hitting it with a massive sledgehammer for just 1 millisecond, could that be the exact same change in momentum, just totally different forces because of the time involved?
Yes, absolutely. The total change in momentum, the impulse would be identical. You transfer the same total amount of currency. But the sledgehammer applies all that force in a single millisecond, so the peak force is astronomical. That is why the duration of an impact defines its destructive power.
Oh, I see. It wouldn't just push the car, it would smash a hole right through the trunk because all that currency was spent in 1 millisecond.
Exactly. You either spend your momentum slowly and safely, or you spend it all at once and destroy whatever's in the way.
That is a great way to put it. All right, moving to the next slide. Slide 5, the grand rule of conservation. We've got this visual of a balanced scale with blue spheres before and after a collision.
This is the core premise of everything we're talking about. In an isolated system, which means a scenario where the net external force is zero, the total momentum remains absolutely constant.
So nobody from the outside is interfering, no friction, no gravity dragging things down.
Right. And if we connect this to the bigger picture, the universe always balances its books. Always. No momentum is ever magically created out of thin air in a crash, and none is ever destroyed.
It just moves around.
Exactly. It gets transferred from one object to another. If you add up the total momentum of everything before the crash and add it all up after, the number is identical. The ledger is perfectly balanced.
I love that. Okay, so moving to the next slide, slide 6. This is a tale of two collisions. We are comparing elastic and inelastic collisions.
Yeah, and the key here is that momentum is conserved in both types. The universe always balances the momentum ledger.
Right, but kinetic energy is different. The slide notes that kinetic energy is only conserved in elastic collisions, where objects bounce perfectly, and it's lost to heat or deformation in inelastic ones, where things crumple or stick.
Precisely.
Let's look the math for absolute beginners. Moving to the next slide, slide 7, the elastic bounce. We have a big mass, labeled 2 meters, moving at 10 meters per second, hitting a resting smaller mass.
And because it's a perfect bounce, no energy is lost to deformation.
Right. So the math on the slide shows the final speed of the smaller mass becomes 7.5 meters per second. They mathematically trade velocities without losing any energy. It's a totally clean handoff.
A perfect transaction. Yeah,
Yeah.
but real life is rarely that clean.
Which brings us to the car crash. Moving to the next slide, slide 8, the inelastic crunch. We have a 2,000 kilogram car going 30 kilometers per hour, and it rear ends a stopped 1,000 kilogram car.
And this is an inelastic collision, so they don't bounce, they crumple and stick together.
Here's where it gets really interesting. The math on the slide shows they lock bumpers, and their mass combines. So 2,000 plus 1,000 equals a 3,000 kilogram entity. And to perfectly preserve that initial momentum, they slide forward together at exactly 20 kilometers per hour.
Yep. The kinetic energy was heavily spent crushing the metal and generating heat, but the momentum ledger balances flawlessly. The math works perfectly every single time.
That is wild. You just combine the masses and track the currency.
It's just that simple.
But wait, both of those examples were in a perfectly straight line. Moving to the next slide, slide 9, expanding horizons. Real life isn't on a straight line. Crashes happen at angles.
They do, and the grand rule still holds. But you have to track momentum on different axes. Momentum is conserved independently on the x and y axis.
So the geometry of the impact matters, but you just balance two separate ledgers.
Exactly. The up and down y-axis ledger and the left to right x-axis ledger both have to balance independently. The universe is a very meticulous accountant.
Okay, moving to the next slide. Slide 10, center of mass. The slide shows masses of 4 kilograms, 2 kilograms, and 6 kilograms mapped out on a grid.
Right, so when you have a messy system of multiple parts, tracking every single piece is a nightmare. The center of mass is the exact mathematical anchor point of the entire system.
So it's like finding the exact balancing point of all those scattered weights?
Yes, it simplifies everything. You can calculate the movement of that entire scattered system as if all of its mass was concentrated right at that single anchor point.
Which brings us to a really crazy visual. Moving to the next slide, slide 11, system dynamics. It's a tumbling baseball bat flying through the air. Now, if I throw a spinning bat, every single splinter of wood is flying in a different chaotic direction. The handle is whipping one way, the barrel the other way. How can the math possibly track that?
I know, it looks impossible. But look at the text on the slide. Internal forces cancel out.
Wait, really? How?
Because for every part of the bat pulling in one direction, another part is pulling back with equal force just to keep the wood from flying apart. To the universe, a twisting, chaotic system is just a single point of momentum. Its center of mass moving in a beautifully smooth arc. The net external force only acts on that center of mass.
Oh, wow. So the universe just completely ignores all the internal spinning and drama, it just sees the anchor point.
Exactly.
Wow. Okay, well, we are moving to the final slide now, slide 12, the blueprint of motion. So what does this all mean?
It means that from a single particle to an infinite number of interacting masses, the ledger is always perfectly balanced. Momentum drives the universe. Underneath all the apparent chaos of our physical world, there's this unbreakable, elegant order.
That is just incredible. Now, a bit of housekeeping for the students in the audience. If you want to review this, search for the creator on YouTube at Dyes, that's Dies, at Dyes Learning Stuff.
Yes, and if you have questions, send your comments to dieslearningstuff@gmail.com.
And please remember to use your school email and include your complete name and class section so you get proper credit.
This raises an important question to leave everyone with. If the universe views incredibly chaotic, tumbling systems as just a single, smooth point of momentum where all those internal forces cancel out, how might that apply to us?
Oh, I like where this is going.
I mean, we are complex, messy systems full of internal conflicts, right? But to the wider universe, maybe we are simply moving forward as one unified entity on a single path.
That is a fascinating way to look at it. All our internal chaos just cancels out. Thank you for joining us on this deep dive into the mechanics of impact. We will catch you next time.